So welcome to the 16th lecture. This is the 16th lecture of this course, and before I come to today's lecture, there was a minor error in this problem. Prove that this De Morgan theorem. There's a minor error here, that is a 0.1 a bar dot b bar 0.1. This should have been, in spite of 1, this should have been 0 here, and rest everything is okay. So let's come to today's lecture. I started with the logic gates with you. AND gate, OR gate, NOT gate, along with the truth tables I discussed with you in the 15th lecture. There's OR gate, there's AND gate, NOT gate, along with their truth tables. Then I discussed some derived gates as NAND gate, NOR gate, and XOR gate with you. Let's look little bit to these gates again. NAND gate and NOR gate especially. See, I told you about the NAND gate. If you look at this NAND gate, let me write this NAND gate here. This is NAND gate, and the symbol for this NAND gate, if you remember, the symbol for NAND gate is this. I am dealing only with two variables, otherwise it can be n variables here. I told you any gate, multiple input and a single output except NOT gate. So if we have two inputs A and B, the output Y is A dot B, A and B whole complement, whole bar. Now just see, this Y is equal to, this Y is A dot B whole bar. Now if I expand this by De Morgan theorem, I can say that this A dot B whole bar is equal to A bar plus B bar here. Now this A bar is a complement, it is a NOT operation, this is a NOT operation, and this plus sign indicates a OR operation, means this can be represented. If you see this overall, this particular function, this can be represented with the help of, suppose I need A bar. How will I obtain A bar? With the help of NOT gate. It means I can represent this as, if you see, this can be represented as in this form. If this is A, so naturally here you will have A bar, this A bar. And if this is B, here you have, if this input is B, for B bar I need a NOT gate here. So this can be written down as B bar here. Now I am interested in a function A bar plus B bar. So A bar plus B bar means A or B. I apply a OR gate here. I apply a OR gate here, and this is A bar plus B bar. Now in spite of showing complete NOT gates, I'll simply represent this. I can say that this figure is equivalent to, see, this is OR gate here, you have this OR gate here, look at this. This is OR gate, and in spite of showing this complete NOT, this is AND and a NOT gate, in spite of showing these NOT, we simply show the bubble of these two NOT gate here. And I say that this is A and this is B. So finally this is your NOR gate, NAND gate. So NAND gate can also be written down, can also be expressed as a bubbled OR gate. It's a OR gate and it's a bubble here. So it is same thing here. This is nothing. It is A bar plus B bar, and which is equal to A dot B whole bar, which is a NAND gate. So NAND gate either can be represented this in this way, or although the formal definition is this one, formal figure is this only, but it can be represented in this form also. Similarly, if I talk about NOR gate, look at NOR gate. This NOR gate. NOR gate, the symbol for NOR gate, as I told you, that the symbol for NOR gate is this, OR followed by a NOT gate, and I am showing only the bubble of a NOT gate. And if you have two inputs A and B here, this output Y is equal to A plus B whole complement, whole bar. A plus B whole bar. Now I am interested, look at this function again, Y is equal to A plus B whole bar. This Y is equal to A plus B whole bar or whole complement. By De Morgan theorem, this can be written down as A complement dot B complement. Now if I want to realize this with the help of basic gates, AND, OR and NOT gates, so see, this A bar, this is B bar, means this is NOT operation, this is NOT operation, and here it is a AND operation. So I am interested in A bar, means again if I have an input A here and an input B here. So for A bar I need a NOT gate. A complement I need a NOT gate. For B complement I need a NOT gate. And for this dot operation I need a AND gate. And now this output is, this is here, at this point you have A complement. This is A, means at this stage you have A complement, and at this stage you have B complement, and here of course you are getting A complement dot B complement here, which is equal to A plus B whole complement. Either you write in this form or in this form. So this is also representing a NOR gate, or equivalently I can represent this as, this is equivalent to, this can, in spite of showing the complete NOT gate, you have an AND gate here, you have an AND gate, and in spite of the complete NOT gate I show only the bubbles of this, these two bubbles of NOT gate, where you have these two inputs A and B. So this NOR gate can also be represented as a bubbled AND gate, and this output is nothing, it is A plus B whole bar. You can say it is A plus B whole complement, which is nothing but simply NOR gate. So this NAND gate and NOR gate can also be represented in this form. Many times it is asked in the competitive exams also. Now next, let me discuss the next topic with you, that is we will discuss SOP form. SOP form. The SOP stands for sum of product. Sum of product. The sum of product means a Boolean function can be represented in two forms. One is called the SOP form and the other is called a POS form, is named as POS. This POS stands for product of sum. Product of sum. Now what is the sum of product and product of sum? See, any Boolean function is nothing, it is a function of certain variables. And suppose I say that you have a Boolean function f, which is a function of suppose a, b, c, three variables. If it is in the form of suppose a dot b plus b dot c plus say c dot a, this form is called a sum of product. Means you have a product. If you see that this is a product here, this is a product, suppose I say this is a product P1 here, this is another product, this is P2 here, and this is another product, say this is P3 here. So it is sum of certain products here. I can say that this is, if I can represent this as a sum of certain products P1, P2, P3, or I say sum of Pi, P1, P2, P3. It is sum of certain products here. This is called sum of product. Or I can say that this can be represented also as a product of sum. Product of sum means, again suppose I say you have a Boolean function which is a function of certain variables a, b and c. The literals are variables are a, b and c, and if I represent this as you have some sum a plus b dot b plus c dot c plus a, means you have a sum here, you have a sum here, you have a sum here. This is one sum. Suppose I say this is sum, this is one particular sum, I name this as S1. This is another sum, I name this as S2, and suppose I say that this is S3. These are the three sums, or it can be number of sum here, or it can be in the complemented form here. Somewhere you can have a bar here, c bar here, you can have a bar here, but the point is that you have a sum here, another sum, and product of these individual sums is called the product of sum. That is, I can represent this as, this can be represented as product, means it is represented by pi, a product of certain sum Si. Although basically there are these two forms only, but there can be a mixed form also. Mix one. That is, suppose I say that f is a function of a, b C. There is a Boolean function which is a function of A, B, C, and suppose I say it is equal to A dot B plus C. This is a mix. This is a sum here, this is a product here. So this is sum of product and product of sum. Now let's come to this realization of this sum of products and product of sum by gates. That is realization pen is not working properly, so I'm using another realization of SOP and POS form by logic gates, Now let's come to this. What do you mean by this term? That suppose I say that you have a function, suppose I say that I have a function, this f is a function of ABC. F is a function of ABC. Suppose I say that is the case, and I say that this f is equal to AB plus BC plus say CA. Now I can represent this with the help, I am not using any, for simplicity I am not using any bar right now, means I am not using any complement right now. So this can be represented as with the help of, look at this, this is a dot here. If you see, when nothing is mentioned here, it is a dot, this is a dot, and this is a dot here. So for this, this is an AND operation, this is an AND operation, this is an AND operation. So what I do, I take an AND gate here. See how I realize this. I take an AND gate here for this AB. This is AB here. For BC, I take another AND gate, and for CA, I take another AND gate. If you see, I take, this is A, this is B, this is C, again this is B, and this is C. Then you have CA. And means AND gate for this operation, AND gate for this operation, AND gate for this operation, and overall this is given to a OR gate. This is called the realization by basic gates. AND gate, and this much. Similarly, suppose I have another function. Suppose I suppose I have another function f. Let's take another problem here. Let's say f, which is a function of ABC again. And suppose I say it is equal to A plus B dot, say this is a B plus C dot C plus A. How to realize this? First of all, you just see how many sums are there and how many products are there. There are 3 sums and overall 1 product here. It is a POS form. There is a SOP form and there is a POS form here. Now for this particular function, if you see that for this particular function I need a OR gate. For this particular function I need another OR gate. For this particular function I need another OR gate. So if I realize this, if you see, if I realize this, I need a AND gate, sorry, OR gate for this A plus B. These are the 2 inputs, A and B. These are 2 inputs, A and B. So here I will get A plus B. The output of this stage will be A plus B. The output of this stage, I need B plus C. So I apply B here and C here. So output at this stage is B plus C. And I use another OR gate. The output at this stage, I need C plus A. So I apply the input C and A. So output here will be C plus A. And overall I need the product of this. I need the product of this, which is equal to AB dot BC dot CA. So I need a AND gate for this, and I simply apply a AND gate here. So this is my final output F here. As I get this final output F here, just if you see here. In this case, I obtain this F here. At every stage I got a product. This is AB, I'll obtain here A dot B. BC, this is B, this is C. I'll obtain B dot C here. This is C, this is A. I'll obtain C dot A here, and overall this is my sum. Now, if I want to realize this, realize how SOP form and POS form, just observe one more thing. I apply same kind of inputs here. Before I come to universal gates, let me give you an idea about this. What I do, simply that in spite, I apply same thing here. In spite of this, I apply a NAND gate here. Just see. I apply a NAND gate here. A NAND gate at this stage. And a NAND gate at this stage. This. And I apply the same inputs here. This is AB. This is BC. So I'll apply B, C. And this is C. And this is A here. Now, what I do, in spite of this also, I use a NAND gate. Just see, I am using a NAND gate here. Let's see what will the output here. What I have done, in spite of this and this gate, I have applied a NAND gate here. In spite of this gate also, I have applied a NAND gate here and applied the similar inputs here. Now look at this, what will be the output at this stage? The output at this stage is A dot B whole bar, whole complement. This will be B dot C whole complement. This will be C dot A whole complement. I hope this is clear to you. Now suppose I say, I name this as, suppose I say this A dot B whole complement is equal to some another function P. Suppose I say that this function is Q. And suppose I say this function, this complement is, this particular function is R. So naturally at this stage I'll get P dot Q dot R, P dot Q dot R whole complement. Suppose I say that this is my output. P, Q, R product and a bubble here. So it is whole complement here. Now I expand this. I expand this by Boolean expression. This will be P bar plus Q bar plus R bar. I hope this is clear to you. P bar plus Q bar plus R bar. I have expanded this by De Morgan theorem. A plus B whole bar. Yeah, A plus B plus C whole bar is equal to A bar plus B bar plus C bar. And now I substitute the value of P. What is P? P is AB bar. P is A dot B bar, but it is P bar, it is whole bar. Plus this is Q is BC bar and it is whole bar, plus R is CA bar and this is whole bar. And I told you that A double bar at any stage, if you have a function A double bar is equal to A. Complement of complement is the same function. So A double B whole bar is equal to A dot B plus B dot C plus C dot A. I hope that, and it is what? This is the same function F. This is nothing but it is simply equal to the same function F here. So I obtain the same function here. So I can say that any SOP form can be implemented with the help of this NAND gate only. Any SOP form can be implemented with the help of NAND gate only. Now coming to this problem again. Let's come to this problem. Same here. Now in spite of all these gates, what I am doing, it is a POS form. This form was SOP. This is POS form. Now look at this POS form. What I am doing, I am replacing all these gates by NOR gate. That's all. In spite of this gate, it is a NOR gate. In spite of this gate, it is a NOR gate. And in spite of this gate also, it is a NOR gate here. And the same inputs, that is AB. Then you have BC here. The input to this is B and C. The input here C and A. And in spite of again giving it to a AND gate, I give it to a NOR gate only. Here also I apply a NOR gate. Now let's see what will be the output at different stages of this. The output at this is OR A plus B, since a bubble here, so it is A plus B whole bar. At this stage you will have A plus B whole bar. At this stage, B plus C whole bar, and at this stage it is C plus A whole bar. And now again, suppose I assume that this function is equal to P, this function is Q, and suppose I say that this function is R, that is C plus A whole bar is R. So at this stage you will have P plus Q plus R whole bar. Again, if I expand this by De Morgan theorem, this will be equal to P bar dot Q bar dot R bar. De Morgan theorem says that A plus B plus C whole bar is equal to A bar dot B bar dot C bar, and now I substitute the value of this. Again double bar will be same, so you will get the same function, that is this will be equal to, finally it will be equal to A plus B whole double complement dot B plus C double complement dot C plus A double complement. So it will be finally equal to, if I say that this will be finally equal to A plus B dot B plus C dot C plus A, and which is equal to this plus A, which is equal to the same function F. So finally I can say that any SOP form, if it is in SOP form, can be implemented with the help of NAND gate only, and a POS form, the SOP form. The SOP form can be implemented with the help of only NAND gates also. Of course it can be implemented with basic gates, but it can be implemented with the help of NAND gate only, and any POS form can be implemented directly with the help of NOR gates only. So I'll stop at this point. In the next lecture I'll deal with these gates only, and especially with the universal gates. So thanks for the time being.